All right, everybody, so let's continue on thinking about population growth models. Now, one thing that I left you at in the last lecture was saying that the logistic growth curve was essentially what we call a equilibrium model. Now, what that's meaning is we have this stable point. Up here at this carrying capacity, there is a stable point, okay? Given the logistic growth curve, as population grows, it will approach the carrying capacity and then stay at that forever. Okay. A lot of our models need some sort of equilibrium, need some sort of stable point for species interactions to actually matter. Okay. So whether we're talking about logistic growth or competitive exclusion, the systems need to have some stable point or some time where the numbers can converge on something. So in the example of the classic paramecium, where conditions or experiments where they were looking at how these were competitively excluded, where paramecium cladatum eventually, with enough stable time, went to extinction. So this equilibrium view is there's a lot of different models that use this. Yeah, again, that competitive exclusion, the logistic growth, and then Lotka-Volterra, that's a model we might get into in this class, looking at predator and prey kind of and competition. So the thing is, we can see some of this equilibrium view in lots of data sets. Okay, so this is the classic data set of we've looked at it before, but wolves and moose on Isle Royale in the middle of Lake Superior, right? And what we can see is there are some times when wolves are high, the red line, the moose are low. Now realize that these are not the same scale, right? So that we go 500, 1,000, 1,500, and there's 10, 20, 30 wolves. So there's really very few wolves on this island, but it's enough, that there's to show the predator-prey interactions. And what we see is, again, when wolves are high, moose are low. When moose are high, wolves are low. Now that's kind of a classic example or a showing that with higher numbers of predators, we expect lower numbers of prey. That's an equilibrium kind of it's a characteristic of an equilibrium model. The thing is, a lot of newer ideas have kind of coming in with that. The idea is that ecology is not driven by all of these processes that work at equilibrium conditions, but there's a lot of non-equilibrium stuff. Okay, basically random fluctuations due to could be weather, and so let's go back to this wolves and moose, right? And we see here that a severe winter here basically kills off a whole bunch of moose. Okay, and so there's not only predator and prey affecting this population, both of these populations, but there's weather or random things like 3 wolves die in a flooded mine. Okay, so 3 wolves might not matter, but when you only have here 15 and now you only go to 10, that's a big deal. That's a large reduction in predation. So there's lots of things that can affect populations that are not just these density-dependent equilibrium processes. Combine that with, for a long time, there really wasn't that much evidence for density dependence. Equilibrium models have oftentimes just pretty much shown to be useless in the real world. Now, why did we spend a bunch of time talking about exponential and logistic growth if there's a lot of ecologists out there that say it's useless, right? Well, to answer that, let's just kind of look at, which one of these things is true. So this argument has been debated in ecological literature for a long time. Basically, through the 50s and 60s, it was kind of all these equilibrium models, competition, predation, are affecting population numbers. But what we see is, so then kind of like 60s in there, a lot of people came in and said, no, it's actually non-equilibrium processes, these random factors that come in, and weather comes in and wipes out half the population. It's that kind of thing that is controlling population numbers. And this is really a false dichotomy. You can't say that it's one or the other. So, which one is true? A lot of people say, well, it's somewhere in the middle, right? And this idea of the argument to moderation, this is a logical fallacy where it's common where if two different people bring an argument or a side of an argument, someone says it's black, someone says it's right, people oftentimes go, well, gray is probably true, right? A mixer of equilibrium and non-equilibrium in this case is true. And that's also false, right? Just because two people bring you two different sides doesn't necessarily mean the middle is actually true. What we see is sometimes it might be density-dependent equilibrium processes. Sometimes it might be non-equilibrium processes that are controlling populations. It just kind of depends. So when we see a population, let's say, of elk here fluctuating wildly through time, there might be in this example equilibrium processes going on. There might be non-equilibrium processes going on. So it might be both of them. It might be a certain population is always, or a certain species is always controlled by equilibrium processes, or another different species in a different area might be non-equilibrium controlled. So it's kind of like just really dependent on the scenario and dependent on the species and the certain conditions of the ecosystem. So when I use this phrase, density dependence, what I'm really talking about is a functional relationship between per capita population change and population density. So what that means here is, in the logistic growth example, the population change is dependent on where we are on this y-axis, right? So population change at really low numbers is really slow because there's just, even though they're having the maximum number of babies, there's not enough babies or not enough adults to really increase the population very much. But then we have an fast increase when there's decent number of individuals. So if the adults, there's some medium number here, there's a lot of adults to have babies, but there's also still a lot of resources left. And so then we get into this negative density dependence, where up here in this top portion of the curve, we get a huge impact of competition, parasitism, predation, all sorts of different density dependent processes. But we have to remember that density dependence isn't necessarily always negative. There's plenty of times where we can have actually the instantaneous growth rate be increased as a population grows. So these are in organisms that use a lot of cooperation, shared defense, or like they look for food together, or you can find a mate easier. So that, this increased mate finding. It might be really hard to find a mate down here when, very few individuals are spread across the entire ecosystem, and it might be actually relatively hard. But up here, it's much more easier, which will increase the population faster than that original R number. So where we see probably the strongest effect of this density dependent is these negative density dependent things at the top of, when a population is getting close to this carrying capacity. Where there's little space, little food, you get really high competition. Excuse me. And we've pretty much found this across all sorts of different areas, and it's relatively experimentally sound. And what I mean by that is we can see there's been plenty of experiments where we do find this density dependence. So when you go back to that question of is the ecology of systems controlled by density dependent or these non-equilibrium factors? The answer is it depends. Yes, certainly we can find density dependence. It just kind of depends on where we're looking and what type of species and what organism we're looking at. So let's bring this idea of density dependence up to a community level, because we generally think of density dependence just in a single species population. But when we think about it in a community level, we got to think about a community level carrying capacity. Okay, so we're no longer thinking about a certain ecosystem can hold this many, like it's not just a number of a population. What we're thinking about is a community can hold a certain biomass of organisms. Okay, and what we see is that one species, if you increase one species, because the ecosystem can only hold a certain biomass, if you have an increase in one species, it means you must have a decrease in the others. And the way we can think of that is think about a piece of pie that isn't necessarily divided up equally, but so this is the resources that go into, or just the amount of biomass, let's say, that go into all of the species in the community. And this would be the most abundant member of the community. I don't know what's next. This one, but then you have some species with smaller pieces of the pie. Because this pie then is bounded, it's not infinite. What we see is if one species starts to take up a bigger piece of the pie, there's less left over. So if this most common species starts to get more and more common, that means there's going to be these pieces need to, kind of by definition, get smaller. And one really interesting place that we see this is on islands. Okay, so we see these density compensation, on big islands in the ocean. Okay, now what we think of it as an island, because it's isolated and out, in the middle of the ocean. It doesn't even need to be far from the ocean, but there's not as many species there. So if you think about go back to this piece of pie, essentially the whole entire pie might only be inhabited by one species. So we oftentimes see the density of a single island species equal the density of many mainland species. So we see this with seabirds on islands. Like you can have super high densities of seabirds because there's basically nothing else there. The entire pie is taken up by these seabirds. Another example is the Hawaiian hoary bat. It's the only bat species that is native to the islands of Hawaii. And we see huge numbers of this single species of bat because it's not competing with any other bats. So it can have really high numbers. And so that's showing this basically community level carrying capacity can be is kind of borne out with those island species, where we see this piece of pie, taken up by just a few species, and they can have much higher numbers than you would expect on a mainland. Now, one open question, and I kind of want to leave you with this idea, is that ecologists really haven't figured out how strong density compensation is. Okay, so when we think about these long-term data sets and looking at, in this case, hares and lynx, it's really hard to say what is controlling these numbers. Okay, is it the predation on the hare from the lynx, or is there some environmental component in here? And there's been lots of experiments basically gone out searching for the answer to this question. And what we know is that yes, density compensation exists, density dependence exists, but it's not just this completely overriding factor that is common in every single system. We need to figure out and do more experiments to try to figure out how strong density dependence at the community level actually is. All right, with that, see you later.